Hello, Professor. We are go.
Hello. Stream is running. One moment, I will put the link to the study system. 1 second. Yes, it's ready.
Yeah, already on, Professor.
Yeah, okay. Zoom.
Pabeidz.
Kur, tūlīt sāksies.
Es
Vēl 2 stundas.
Tur vienkārši attēlu domāju, bet nu labi, tas tā.
Bla.
Vēlāk.
Vēl bišķiņ jāpastāst. Vēl amplitūda frekvences raksturliknī jāparāda studija.
Skaidrs. Tur cilvēkiem būs ko domāt.
Un reakcija uz vides izmaiņām.
Skaidrs.
Tur vēl daudz interesanta. Ok, вот он. Vicky, where am I? Yeah. So, current related to the current at a frequency equals to resonance frequency will be 1 against 1 plus c squared, or approximately 1 divided by 1 plus double quality frequency and square. If we want to use such circuit as a filter, or if we want to use it to somehow condition our signal, so transfer function in the middle, we can take output voltage from coil or from capacitor. If we take output signal from capacitor, it will be transfer coefficient by nature it's a function of frequency. This way is more correct. So, by E, or quality omega 0, omega, and here we'll have square root 1 plus c squared.
So that is the resistance across the capacitor, right? The first one.
Where resistance? Where resistance? No. It's not a resistance. It's a transfer factor. It's idea. We have E as an input source, and output we take from capacitor's voltage. Result can be denoted as a transfer coefficient Chi. And we will see something usually in all literature you see set of chart like this. More correct. Think like this. They are drawn. This one Q prime better than they are drawn at the different something like this. All these charts are drawn at a different quality, but they are all drawn in a relative frequency around the resonance frequency. And it's a tradition. It is in relative values, it is 1. Usually it's current against current at the resonant frequency. Transfer coefficients will have the same absolute value, and this one is relative, they are normalized to draw a family. In nature they look a bit different. I'll show if you give me small time. Okay. Another way to get output is use a coil voltage. Coil voltage or coil transfer coefficient, which is absolute value of coil voltage against absolute value of the input, really will be the same. Square root 1 plus c squared, or if you want, it will be current against current at omega naught at resonance regime, quality omega related omega 0. At a point of resonance, when frequency equals to omega 0, they both are equal to the quality. the form of characteristic. So, the form of characteristic, something like this, it's quite high quality. Okay. Some coefficient. This form allows us to think what such system, sequence contact, can be used as a band pass filter. When we have idea LPF suppresses high frequency, HPF suppresses low frequency, band pass filter, ideal band pass filter from omega low to omega high cuts off, so BPF, band pass filter, from all frequency range cuts off some frequency band. So such figure in some way is near to the ideal band pass filter. Of course we need LE as low as possible because it's the high internal resistance of source, the wide will be this characteristic. And as a bandpass field, it will be worse. It's a reduced quality. My circuit, this circuit I have assembled, works a bit different. I have source, maybe it's internal resistance, and two branches. This will be A point. This is coil, this is capacitance. This is 1, this is 2. Point B. This way. I have a contour of parallel resonance. If you remember basics of electrotechnique, I can write down a condition, what imaginary part of conductance, of input conductance between A and B is 0. This will give me a frequency of current resonance. And it's again is LC. At the point of resonance, the internal contour resistance is very low and current achieves quite significant values. That's why such parallel resonance is called resonance of currents. resonance of currents. Input resistance, we can write input resistance omega L plus 1 against omega C divided by L1 plus L2 plus omega minus 1 against omega C can be approximately written as L divided by capacitance plus 1 omega minus 1 against omega C. At the point of resonance, at a frequency equals to omega 0, input resistance will become purely active, quality multiplied by characteristic resistance. It is very typical for characteristic resistance being some 100, 200, 500 ohms quality of good qualitative content above 100. And resonance resistance of parallel contour maybe 100 ohms, maybe 10 ohms, very low.
Professor, R is just the RI resistance or everything?
Sorry? I badly hear you.
The letter R in the last one, where rho squared over R.
Rho square or quality multiplied by characteristic resistance, or it's also sometimes called wave resistance.
So that
It's square. It's a square characteristic resistance square divided by active resistance.
Active resistance. Yeah. Okay. So that is active resistance of the coil.
Yeah, it's a in general it's coil plus wires connected capacitor to the network.
Okay.
In general, it's a coil. Okay, I'll prevent doubling of sound. When we analyze areas near the point of resonance, meaning omega is much smaller than the resonance frequency, show the small deviation from the central frequency. Input resistance can be impedance written as square divided by R plus, say 1 second, 1 plus C or its absolute value can be approximated as at the frequency omega divided by square root 1 plus C squared. Resonant characteristic is a voltage UA against UA at the frequency omega 0. Resonant characteristic. It will give us transfer function. So, voltage let's assume what we have ideal generator. So E generator is constant. Let's assume we have ideal generator, meaning what generator internal conductance is zero. Sorry for that. In this case, in such case, voltage will be generator current ZAB input or current ZAB at a frequency omega 0 divided by 1 plus Xc. And resonance characteristic can be constructed in its ideal. So voltage divided by voltage at a point of resonance will be 1 against square root of 1 plus Xc squared, or approximately 1 divided by square root 1 plus double quality frequency shift relative frequency shift and square. It's the same characteristic of sequential resonance contour. So in general, characteristics do not change. It sounds strange, but general characteristic is the same. Only for sequential contour, for voltage resonance, ideal case is when the source internal resistance or internal impedance is zero. For this case, ideal, for parallel contour, ideal case will be when generator output resistance is infinite. Now, transfer function. Transfer factor, if we take a coil voltage, is the same if we take capacitor voltage, and it's equal to let's say EL against current, or approximately U and omega equals to omega 0 to point of resonance, quality omega against resonance frequency, or contour quality omega 0 divided by omega 1 plus square. Quality, the quality factor itself, overall or equivalent quality will be characteristic of wave resistance divided by both resistance plus square of the characteristic resistance divided by source internal resistance. Overall quality. Now it would be better to investigate it, isn't it? How can we investigate or research a contour? We need an instrument. We need an instrument to analyze process as a function of frequency. How? We need a special tool or instrument called analyzer of amplitude frequency vectorly characteristics or body plotter. How can we do it? It is old way and new. Old way, classics work like this. First, we need a source, better use a source of triangular voltage, but in fact we can use any, yeah, it's working. We can use, maybe this one, it's not very principal, but working area should be linear. Then its signal will be used in two ways. Let's take another. It's a generator controlled by frequency. Which frequency is controlled by the first generator. Its signal supplied as an input signal to the test object. To prevent influence of the test object input impedance, special stabilizer scheme is implemented, which controls voltage of generator. It just changes voltage of generator to maintain voltage at the input point constant. Also, well-known CRT tube is used. The control generator is used to drive the X channel. Output signal of the tested object is passed through the absolute value function and supplied to the Y channel of CRT. result, we will get a research figure. Horizontal movement is determined by the sawtooth generator. But since the frequency of the control generator is direct function, directly bound to this voltage, in reality it will be frequency around some point, but it will be frequency. Y vertical channel is reaction of the test circuit. Since we stabilized generator voltage, it will be what? Sx, Sy against Sx in some scale factor, or absolute value of transfer function. So we just said we will be able to monitor transfer function in dynamics live. Let's try. Bring me one second. I'll get camera. Hold. We are showing yes. Brighter and Maybe I can come a bit closer. Hey, I wanted to come a bit closer. This way. Yeah, characteristics. We see something, but what it is? Hey, camera. Come on. 1 second. Yeah. I hope you can see. I have an assembly of coil, quite high quality coil, in opposite direction, yeah. It's made of the copper ribbon attached to the steatite. It's a special kind of ceramics. It's something like a small pipe. See, it's empty pipe, and copper ribbon on it. Quite high quality coil. In parallel, I have an A capacitor. I can change. Hope you can see. I can change its capacitance. And you see, I increase capacitance, and resonance characteristic or transfer characteristic goes down. Also, you can see it's lower. You see quality goes down. Increasing capacity, I also increase area of the active veins, and this increases losses in the contact. It's the second resistance increase force, because increase area of active veins, area where the current flows. I can try another experiment. This one is a ferrite. It's a material with a good magnetic conductivity. Look what happens. Big. Oh, 1 second. Oh. Yes. Look what happens when I increase magnetic conductivity of my coil. You see, inductance, magnetic conductivity increases, inductance increases, resonant frequency decreases. You see? And also charge it goes down. Losses. It's like increase R2. Direct, take a look. I'm increasing R2. See, characteristic goes down. Amplified to the same. I amplified it. Now it's wider. See, character. I introduce active resistance. I have increased. It's R2. Yeah, I have increased R2, and you can see what in relative value we'll see it's a wider VMI. Mi. We will see the wider characteristics. They are drawn all in relative values. In nature, we take them from 0 and they go down and become wider. If we draw in relative characteristics, they will come from the top. Near 0 resistance, of course it's not 0, some resistance remain, some 10 ohms plus. That's how active resistance changes characteristic. I can also use this object. It's an aluminium pipe. What will happen? Of course, loss are increased because current flows in the pipe. But also, you see, introduction of the short circuit object, in fact, works only only surface of this pipe works, but it's short circuit and it decreases magnetic energy stored in coil. And you see, losses increase, but frequency goes up, frequency decreases. Maybe I don't have a scale here. Wait 1 second. You can see now appeared. Let's see. Disappeared, appeared again. They're small. This like scratch on the line. Each such scratch is 1 megahertz. To understand the scale, it's approximately 1 megahertz per centimeter. Horizontal scale now. Just for understanding, the central frequency is 20 megahertz. Aluminium or this object, brass screw, increases resonance frequency. Ferrite, magnetic conductive material, decreases resonance frequency because increase inductance and increase overall contour inertia. Wait 1 second. This one is parallel. We saw a parallel contour. The coil is in parallel with capacitor. Wait 1 second. Where is my series? Here it is. It's a previous model, coil and capacitance. This one is for series resonance. What we get? We will get UL. Come on. Here it is. Wait 1 second. Oh. Can you see it? Oh. 1 second. This way is okay.
Yeah, it's visible, Professor.
Yeah.
It's fine.
It's okay for. Then, okay, make this scale better. I'm changing inductance. Oh, I can change custom with my finger. You can see what in general, the characteristic is the same. Or resonant circuit, in most general form, all the circuits, when we have one coil and one capacitor, will produce a resonant characteristic like this. If resistance is below critical. If resistance is above critical, there is no resonance at all. The magnetic core deeper, frequency low. Magnetic core goes up, and resonance chart also goes to the higher frequency, because magnetic conductance of the network decrease. This means that stored energy also decrease, inertia decrease, and frequency of free oscillation goes up. And also resonance frequency. Here it is. Now we saw resonance characteristic for both parallel contour or current resonance and when they are in sequence or voltage resonance. And now I have a question. Half an hour. Should I start mutual couplet network or wait it for the next time? What would you say?
We would like to do that on campus, Professor.
Yeah, it's better what we can see. Next time we can touch it with the finger.
Yeah, that would be nice. For a change. Yeah.
When it was, 3 weeks ago, I made an experiment for one demo, and parallel contact touched me. Okay, it's at the frequency voltage was some 300 volts, but at 200 kilohertz, it's you don't feel it like a shock. Just something burns. Oh, it's my finger. Because see, it says it's called the skin effect. The higher frequency. See, at higher frequencies, magnetic field pushes current lines out of the object. At the low frequencies, current flows through all the conductive object. But at the higher frequency, the closer current will be to the surface. Magnetic field pushes current lines to the surface. So at high frequency, when somebody full enough to touch live parts, gets current to his body. But this current flows at the skin surface on under the surface, but very near to the surface, where there are no nervous connection to the muscles. So you don't get a shock, but current flows and burns. Thermal effects remain. So don't touch live parts in any way.
Of course, Professor. Yeah. Professor, I also wanted to ask you about those questions that I asked. If you can put it on Otis or something when it's available.
Sorry.
Basically, it's like exercises on the.
Yeah. Understood. Okay, I'll do it. Just keep it in. Okay. I need to put them, but before we need before we knew discrete time, Fourier transform, they are useless. Okay, the next we will finish resonant networks. I also need to take Fourier transform of non-periodic signals, and next will be the discrete time.
Yeah.
And not forget example.
Yeah.
Okay, I have it in my plan. Yeah, time is running. Okay, I remember what I need to do. Actually, no, I have one record, but okay. Let me do it in the right way. First, theory, and I'll show the process with example. How? The problem what we will also need a topological analysis, and what? And problem is what bachelor students they get another course. It's called application of computers in the power engineering, and they get topological analysis there. But since you don't have this course, I need this short extraction of from there here. But it's simple. It's simple basis of electrotechnics. Just apply it for solution of the circuits. No problem, it's easy. Everything will end fine.
Yeah, perfect, Professor. Yeah, sounds good, Professor. Then we'll see you next week.
Okay.
Yeah.
This stream I can end.
Yeah, and next week we will start at 12:30.
And then next week, welcome to 320.
Yeah, 320 at 12:30, right, Professor? Or is it? Yeah, 12:30.
Yeah, 12:30.
Yeah, perfect.
Okay, let's.
Okay, Professor. Thank you very much. See you then.
Welcome.
Okay.
Welcome.